Yes. Good afternoon, students. So yesterday we have got one question bank. Okay, from the chapter basics of representation and psychometry. So let us assume that out of this particular question bank, important questions, some questions will may come in the tomorrow's examination. That is in same examination. So whatever difficult examples are there from this particular question bank, I will try to solve these examples, and whatever theoretical questions are there, you solve that questions by your own. Okay, such as this question, explain the schematic diagram of simple vapor compression system. So you can solve this particular question very easily. Okay, I have already explained all these different components which are available in the simple vapor compression system in very detail. So you go through that. Draw and explain in detail vapor absorption cycle. This also I have explained very well, and I hope you have understood this particular question number 2 and question number 3. So you try to explain these particular things very well. Now let us see the question number 1 here. If you see this question number 1, just 1 second. So what is the question number 1? With the help of PV and TS diagrams, explain reverse Carnot cycle with vapor as a refrigerant. Assuming unit mass circulation of refrigerant, derive the expression for COP of Carnot cycle. What are the limitations of the reverse Carnot cycle? So this is the question, and let us try to solve this particular, explain this particular question, so that you can write in examination very well. So this is the question I have answered here. Question number 1. So what is reverse Carnot cycle? Everybody knows what is the reverse Carnot cycle. Okay, it is a opposite of Carnot cycle, right? And if you see this particular diagram on PV and TS diagram, so here if you see there are four processes, that is from 1 to 2 is isentropic compression, 2 to 3 is isothermal compression, 3 to 4 is isentropic expansion, and 4 to 1 is isothermal expansion. Okay, so during this 4 to 1 process, heat is absorbed, and from process 2 to 3 heat is rejected. That is, here there is a condenser. Okay, and here if you see in the TS diagram, the 1 to 2 is isentropic process. That's why S1 is equal to S2. Here we can write this S1 is equal to S2. Okay, I hope you are clearly visible this. And here S3 and S4 are same. Okay, S3 and S4 are same, right? So let us go further. So I have already explained, 1 to 2 is isentropic compression, 2 to 3 is isothermal compression, 3 to 4 isentropic expansion, 4 to 1 is isothermal expansion. Now we have to derive the equation for COP. Okay, we have to find the value of COP with the help of that particular this PV and TS diagram. So we know that what is COP? That is coefficient of performance. That is for, let us consider for a refrigerator. So COP of refrigerator is equal to refrigeration effect upon work done. Okay, everybody knows this formula. So what we have to do? We have to calculate the value of refrigeration effect and work done. So we know that work done is Q supplied minus Q rejected, or here in this case we can take as Q rejected minus Q absorbed. Also we can take here. Okay, and so how to calculate this refrigeration effect? So if you see here in this diagram, this 4 to 1, during this particular 4 to 1 process, a refrigeration effect takes place. So how to calculate this refrigeration effect? So you know very well the value of this ds. What is value of ds? That is change in entropy. Okay, it can be written as dq upon t. So you have already studied in engineering thermodynamics. ds is equal to this particular formula, ds is equal to dq upon t. So from this formula we can calculate the value of this particular dq, that is nothing but your refrigeration effect during process 4 to 1. So from process 4 to 1, if you see here, we can write this as T4. What is this T4? Look at this T4. We can write here T4 as well as we can write here T1, because T4 and T1 temperature both are same. Okay, so refrigeration effect RE, that is equal to Q4 to 1, that can be written as T4 S1 minus S4, or this can be written as T1 in bracket S1 minus S4. Okay, S1 minus S4, or we can write T1 or for T4, or also we can write here, if you see T1, S1 and S2 are same, so therefore in place of S1 we can write down S2, in place of S4 we can write down S3. Okay, both are same. And now how to calculate work done? So Q supplied, that is during process 4 to 1, Q is absorbed, the heat is absorbed by the evaporator, and during 2 to 3 process heat is rejected. So how to calculate this work done? That is Q supplied minus Q rejected. So by using the same formula, we can calculate work done is equal to T1 in bracket S1 minus S4 minus T2 into S2 minus S3. Let us consider this is equation number 2. So but we know that COP is RE, that is refrigeration effect upon work done. So that is equal to T1 in bracket S1 minus S4, that is from equation number 1, upon T1 in bracket S1 minus S4 minus T2 S2 minus S3. Okay, now but this S2 minus S3, look at this S2 minus S3 can be written as S1 minus S4. Why this we can write? Because we know that S2 is equal to S1 and S3 is equal to S4. So in place of this S2 we can write this S1, and in place of S3 we can write this S4. Okay, so other things are same. Now S1 minus S4, if you see in each and every term, this is common, so we can take it common and it get cancelled. Okay, so what is remaining here? T1 upon T1 minus T2. But here if you see, what is this T1? T1 is nothing but your evaporation temperature. If you see carefully in the diagram, this T1 is nothing but your evaporation temperature, which is less than condenser temperature, that is T2. And therefore here we can reverse this particular values, that is T1 minus T2 can be replaced by T2 minus T1, and this is the value of coefficient of performance for the refrigerator. So if you derive this for a refrigerator, that is also sufficient. Okay, if you want to derive it for heat pump, you can also derive it. Okay, but at least one, you have one derivation is needed. Okay, to get the full marks. So that is nothing but T upon Tc minus T. Now if you see this particular equation COP, that is it includes the only temperatures, that is evaporator temperature and condenser temperature. That means COP depends only upon, here this particular equation indicates that COP only depends upon T, evaporator temperature and condenser temperature. This is one limitation here actually. Okay, so this is the first limitation. COP is function of temperature only. Next, if you see in this particular isentropic, reverse Carnot cycle, what is happening here? The application of isentropic and isothermal processes back to back is impossible. Why it is impossible? Because in the isentropic process, the pressure increases fastly, which requires a high speed, and in the isothermal process, the pressure increases slowly, which requires slow speed. So achieving high speed and slow process back to back, it is impossible in real life. Okay, this is the first limitation. And what is the second limitation? In the heat addition and the heat rejection of the heat at constant temperature is impossible, because everybody knows that whenever we add the heat into the system, then definitely temperature increases. Okay, so these are the limitations. So I hope you understand this particular first question carefully. Okay, now let us see the next question, or we will see this question number 2 in the next video. Okay, so please go through this particular derivation, whatever how I have derived this equation. This is very simple question. Okay, and just we have to explain this much to get full marks. Okay, so I hope you understand this. So thank you very much. We will see the next question in the next video.